All right, today, the first half of the class, the main goal is to be able to do what are called approximations using an iterative technique. That's kind of a crazy word. This is the only time in your math lives that you will ever intentionally use an approximated value to do another calculation. As most of you know, whenever you're doing a calculation, whether it's math, physics, chemistry, whatever, if your final answer is an irrational number, you hold on to it as long as possible and then you approximate your final answer. You don't generally approximate as you go because you get the round off errors, right? And every time you use a rounded off number to do the next one, it's a little further off. This is the rare time you're actually going to intentionally use rounded off numbers because we're looking for something different. We're looking for something called convergence. So I'm going to give you a simple picture of what it is we're going to try to find. Let's suppose I just have some random graph and it's doing something like this. Now, my x-intercept right there, the x-coordinate is either rational or it is not. If it is rational, I absolutely guarantee you there are methods of algebra that you can find it absolutely 100% of the time without exception. There is no problem you can't solve and find a rational root. Whether it be factoring or whether it be just something simple, you can always find a rational root. It doesn't require any high-level math. So let's make an assumption. Let's assume that here are two integer values and that's irrational. So let's assume it crosses at an irrational coordinate, which you may not be able to find. Okay? You say, what do you mean I won't be able to find it? Well, something as simple as this, for example, if I said, I want to solve this. You realize how hard that will be? If I want, we're going to do this today, by the way. I have a cosine graph. That intersection is not at a rational number, and there is no algebraic technique that exists that you can tell me x equals. It's not possible. But we'll be able to give a decimal approximation as many decimals as you choose that will be absolutely correct. That's our goal today. So our goal, we're going to start with a simple problem. Our goal is to find this x-coordinate, assuming it's irrational. So assuming I can't say x equals and then give you a whole bunch of crazy-looking numbers. It's maybe beyond what we can do in that regard. So how am I going to do that? Well, again, let's assume it passes between consecutive integers. Because if it passed on an integer, then it's rational. So the first thing I want to do is I will pick a value between these two integers. And without any other reason, I'll just pick the halfway point. So if this was 3 and this was 4, I'll start with 3.5. Okay? So what I'm going to do is pick that value. And let's say that value puts me up here. Then I'm going to draw the tangent line right there. Because I'm going to use a rational number, like 3.5. If I evaluate my function at a rational number, I get a rational number back again in most cases. And then I'm going to draw the tangent line. And here's the cool thing about the tangent line. That tangent line is going to cross pretty close. The x-coordinate on the tangent line, where it crosses the x-axis, will be closer than my original guess of, let's say, 3.5. Okay? This is what's called the first iteration. So I'm going to start with x equals some starting point that's a nice, happy number. Again, it's probably just halfway between two integers, something 0.5.
Could you switch the markers kind of hard to read?
Oh, okay. I kind of need them to be different colors, though. So now the question is, where does the tangent line cross? So let's come up with the equation of the tangent line. Right? That's simply point-slope formula. So the point right here, that point is x naught, f of x naught, which are probably both semi-friendly. What is the slope? Well, that would be f prime of x naught. Okay? So how does the point-slope formula work? I need a point, I need a slope, I have both. So y minus the y-coordinate equals the slope times x minus the x-coordinate. This is the equation of this orange line. Now what I want to know is, where does this line cross the x-axis? Exactly where does it cross the x-axis? Well, isn't it going to cross the x-axis exactly when y is 0? Everybody agree with that? When y is 0, it crosses the x-axis. That's a constant, that's a constant, that's a constant. That's a variable, but I'm going to choose y equals 0 and then figure out what's the value that I will get for x. And that's going to be my next iteration. So if I replace y with 0, let's do this then. F of x naught divided by f prime of x naught would now equal x minus x naught. I'm trying to get x, so let's add x naught to both sides, and then I would get x naught plus, minus, in this case, minus. We have a calculator. Number, number, number equals. This number is probably going to be a long drawn out decimal, which we will choose to round off, and I'll explain where that comes. The number we get, this is going to be our first calculated value. It's called our first iteration. We started with x naught. We chose this value. We didn't compute this value. We computed x1 this way. Now, x1 is much closer than my starting point was. I want to get closer still, so we're going to do the exact same process again, but this time we're going to use x1. So where that was using x naught, we're now going to use x1. I think you're going to see a pattern really quickly. So now I have a new tangent line, and it looks like this. And when I replace y with 0 again, and I solve for x, it's going to look like this. x1 minus f of x1 over f prime of x1. And that's going to be a numerical value. Probably my whole calculator screen is filled up with yucky decimals. And I'm going to have a really clever name. You're never going to figure this one out. What do you think we should call this guy? Call that one x1. X2. Oh, you guys saw the movie. Now, I'm going to continue doing this. This is not hard. But how do I know when to stop? When we get consecutive iterations that produce the same value. That means I'm going to get that value till the end of time. Means that's the answer to the question. But we have to decide first, how many decimal places do we want? Now this is critical because this will change how I do things. Let's suppose for whatever you're doing, you decided 3 decimal places was enough information. That might be overkill. Maybe I need less. Let's just say hypothetically, or the instructor said, I need 3 decimal place answers. So what you're going to do on your very first calculation is round this to 3 places. Then use the 3 decimal place rounded off number to calculate this one, and then do the same. Round this to 3 places. You continue this process until you get the exact same number 2 times in a row when rounded to 3 places. When that happens, and we say it this way, when the n plus first value is the same as the nth value, that means you're going to be there forever and ever and ever and ever. That's the answer. 2 3 decimal places. So generally speaking, if you're asked to approximate a solution, if the answer were root 2, you'd say root 2, but then you could give me a decimal. If the answer was, pi, you'd say pi, you'd give me a decimal. But what if I can't even give you the exact answer because it was so complicated, but I could give you the decimal? Then we're satisfied with the decimal because you can go as many decimal places as you want. Now, the more decimal places that you choose to answer the question to, the more steps this may take. But what you're going to find is this process converges really fast. To converge means this happened. And what you're going to find is in most problems, by the time you're at x2 or x3, you're probably already done. It's not going to take 10 tries. It might only take a couple. It's very, very powerful. This technique is called Newton's method. Yeah, I remember being in his class when he first discovered this. He was so excited, but calculators were still a few hundred years away from being invented. So we could only talk about this in theory, back then, a few centuries ago. I was around. Newton's method could not actually be executed until we had technology. So we only knew this in theory, but now we know it in practicality. So we're going to do some examples, and you have to have a calculator because everything's a calculation. But you're going to find it's really, really simple as long as you don't make a mess of things. All right. Let's consider f of x equals, how about x cubed? Okay. Minus 6x, let's say plus, how about plus 1? All right? Now, I want to find the x-intercept between x equals 2 and x equals 3. I think that's where it would be if I just look at that. Yeah. There's an x-intercept between x equal 2 and x equal 3. How do I know that? Because f of 2 would be 8 minus 12 plus 1, that's negative 3. And f of 3 would be 27 minus 18 plus 1, which is 10. So do you see I have to cross the x-axis between those 2 points? Okay? So, I don't know what the answer is. I know there is an answer. Are we okay on that? We know there's an answer. So, here's what we do. We have to find the derivative because there's a formula that we're going to generate. I'm going to show you every shortcut that is possible. So I need to find f prime of x. And what will that be?
2x squared.
So 3x squared minus 6. And here's how we write it. The formula we developed, this was x2 in terms of x1. x3 was in terms of x2. x4 was in terms of x3, on and on and on and on. I don't want to write a different formula for each one, so we actually write it this way. We say the n plus first iteration is the nth iteration, right, where you just had 1s and 2s a moment ago. Now I'm going to use n's and n plus 1s. F of xn over f prime of xn. So when we started it, we had x0, 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 and this was x1. Then we did x1, 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 and we wrote x2, and so on, and so on, and so on. So here's sort of the general formula we're going to use on every problem. We have to choose our starting point. That's easy. And then we do this. Now, one of the things that I suggest, particularly when you have polynomials, if I use this formula, I'm doing everything correctly, but there's a lot of plugging in. For this problem, the n plus first iteration is equal to the nth iteration minus the original function over the derivative. Where's that? 3. Now, the subscripts actually are quite critical because they're not the same. The subscripts on the right are always going to be one less than the subscripts on the left. That is very, very important. I got to plug in a lot of x's, don't I, on the right side? Do you think algebraically there's anything simple we could do? Maybe to the right side? Put everything on, make a 1 quotient. You'll find that on almost all problems, this will simplify things tremendously. It will reduce the amount of work you have to do tremendously. Right now, I have 1, 2, 3, 4 places I have to put the x. I have to use sets of parentheses because of all the things going on. What if I put that over one common denominator? Let me do that off to the side. I'll just write x minus x cubed minus 6x plus 1 over 3x squared minus 6. How do I do one common denominator?
Multiply upstairs by the same denominator.
Would that work if I do that? So let's distribute on top. What do I got? You never have to do this, wink, wink. I do this every time, and it simplifies things tremendously. So I'm going to have
3x cubed minus 6x.
and then subtract this whole quantity. What do I have left on top now?
2x cubed plus 1. Well, yeah, minus 1.
Minus 1. Oh. Would you say that's simpler than that?
Yeah.
Yeah. Half as many buttons. Yeah, yeah.
Isn't it 3x squared on the denominator, not 2x squared?
What did I?
Denominator.
Oh, thank you. Yes, sorry. I'm like, I have a 3x squared. Well, there, yeah. This, absolutely this was correct. This is way simpler, isn't it? Less stuff. So what I'm going to do is use the simplified version. You notice I didn't mess with the denominator, but I made the numerator a lot shorter. So what is that, 2x, 2x cubed minus 1? So this is what I'm actually going to use when I do my calculations. It's just less work. It's that simple. Now, if I was doing all of this on the computer and I programmed the computer, I don't have to do any of the algebra. I just tell the computer to do the next thing, but that requires a little bit more setup. So where should we start? If I'm crossing between 2 and 3, where should we start? Pretty much always going to be the same thing. Between 2 and 3, probably 0 is not a good answer.
2.5.
How about 2.5? Yeah. Let's start at 2.5. Let's make our first, that's not a calculation. That's a starting point. That's our x0. We're starting there. So I'm going to write it like this. We're going to choose x0 to be 2.5. Now, x1. I'm going to put 2.5 into this and do the calculation. Let's all do that? Because we all want to agree. Tell me when you got a number. So you got 2.37 stuff. Now, I was remiss in this. We have to decide on something. And again, this is actually not your decision. Usually it's the instruction you were given because you're doing this for another class. You're doing this for physics. You're doing this for a chemistry class. And the instructor will say, here's the degree of accuracy that I need in your answer. Here's the degree of precision. So probably the most common would be either 2 or 3 decimals. You can give me as many as you want. What do you want to go with?
3.
Okay, let's go with 3. So we actually need to state that at the very beginning of the problem. This is not something you decide later. So I know that in physics it's pretty common. It doesn't really matter. It doesn't change how we do things, but it does change where I round it off to. So my number looks like 2.3725. So the 3 places, what should it be? Now, by the way, you can't make an error on round off. I always laugh at this one because calculus students are really good at math. They're really bad at things like rounding. There's only one rule of rounding. It's never changed in the history of rounding. And I have a stats class that almost every single person said they learned something different, which is scary because there's only one rule of rounding. You look at the next place, it's either, what, 0 to 4 or it's 5 to 9. If it's 0 to 4, you round down. If it's 5 to 9, you round up. That's it. If you learn something else, you learned it wrong and you're getting the wrong answer probably most of the time. No, it's real simple. My 4th number is a 5, so I go up. And what am I going to write?
2.373.
373. Now, this is not a terminating decimal. I am rounding it off. This is absolutely when you use this notation. You're doing a calculator round off. You're saying, because if I put an equal sign, by the way, there's an equal sign here because it's exactly this number. You only use an equal when it's exactly that decimal. Your first number will always be exactly, and you might get lucky that one of your calculations turns out to be exactly a number. Not very common, but you're probably rounding it off. Now I'm going to do this process again. First round I used this. Second round I'm using exactly this, not my calculator screen. Now this is what's different. You guys know this, that whenever you use a calculated value, you use the whole value, right? You always use the whole calculator screen. You use the answer button on your calculator. It's my favorite button. You don't have to re-enter. That's not what we're doing here. We actually are intentionally using the rounded off value because what I'm trying to do is get that number twice in a row. So we're going to use this number to do our next calculation. And you notice I did not write down what the cube of this was and -1 and divided by. No, I'm taking this number, I'm putting it into here on my calculator, and then I'm writing only the answer that I get. You're doing the whole thing on your calculator. So let's do this number now.
2.362. No, 2.362.
Everybody try this because a lot of you are just watching and you're waiting, but
But then
you
you
want to make sure
Ryan.
you can do this.
Yeah, 16, sorry.
6.1 after that.
You do not need a fancy calculator. So what do you get?
2.362.
Now what do you notice? The movement here, now this movement was much less, wasn't it? What you're going to see is the movement is less because you're getting closer and closer and closer. Do you remember when we did the E, when we did the calculation of E? Remember we kept increasing the number of times per year we were compounding it? And no matter how many times we increased it, remember the changes got smaller and smaller and smaller? Because we converged on our calculator to the E. That's what we saw. So I'm going to use this value now. Okay.
We get 2.361.
I'm going to do 2.362. So what did you get?
2.361.
Are we done? No, every number's changed.
Yeah, you do one more time.
So we're going to do one more time. And what did you get?
2.361.
Let's do it like 5 more times just to be safe. What are we going to get every time forevermore?
2.361.
We're done. The moment you got the same number twice in a row, now you're not getting that?
Yeah, no, I got for X3, I got 2.3615. So it's just.
Oh, I was trusting Chase here. I know that's always a grave mistake. Let me do that one again. Let me plug in my X2.
146.
2.362 cubed minus 1. I just trusted him. I didn't even bother doing the calculation.
I have it as 4 instead of 5.
Yeah, it's 3614689.
Oh, okay. It's 23614. You rounded to get to the 5 and then you rounded again. Oh, your calculator's not reporting enough decimals. Yeah, I gotcha. Yeah, that could be dangerous. Yeah, this is correct. So if we kept going, do you all agree we're going to get this number every time because we're rounding the iteration? What makes this process way different, you have never used a rounded off number with the intent of rounding off everything along the way because you know that would take you away. We're doing just the opposite. Every calculation is getting us closer to the answer. To 3 decimal places, that is the answer. That's not a terminating decimal place, but the 3 decimal places, that is the answer. If we had only wanted to go 2 decimal places, we would have hit it here. You know, that's the thing, is less decimals, you hit it sooner. So we hit it on the 3rd, we confirmed it on the 4th. You have to do it twice in a row. So now, the question was, I want to find the value of x that makes this function 0 to 3 decimal places. So now I'm going to give you my answer. My answer is that x is approximately 2.361. I'm now done. X does not equal that because my answer is not rational. It's rounded to 3. I'm pretty sure I did everything right. Are you happy with pretty sure?
Plug it into the equation.
Plug it into the equation, and what should I see?
0 up to 3 decimals.
Something really small. How's that? Does everyone agree that if I'm saying that's my x-intercept to 3 decimal places, then when I put it in, I ought to get a y value that's really, really small. So let's all do that. Let's take this value and let's put it in here.
What you do?
Now, when I put it in there, a little bit higher up here, sorry. I'm gonna put that value in. I don't ever need to see this. I will assume that you did this. You got something that looked like that. Would you say that's small?
Yes.
Yeah, I'm gonna go out on a limb and say it a different way. If I chose any other number, maybe I went 6.2, 6.0, it's gonna be a little bigger. As I drift further from this, this will drift further from 0. So to 3 decimal places, that's the best answer we can give. Was that hard to do? No, all we needed was a cheap calculator. Pretty powerful. So we mentioned last day, I mentioned the trace key on your calculator, right, for the graphing calculators. This is exactly how it's actually done. Your calculator, if you're actually asking it for an intercept that's irrational, it's literally using Newton's method because there's no other way to get it. We don't actually have a secondary method mathematically to do this. So the incredible thing about this is we've known this for a really long time, but we didn't have the ability to execute this until recent generations because we didn't have handheld calculators. Yeah, we had computers, but they weren't very good for a long, long time. Okay? Pretty cool? All right, let's do another one. You're out in the field, maybe, I don't know, or you have a calculator. I have fun with this. I remember when calculators first came out. They added, subtracted, multiplied, and divided with no order of operations. And they're really big. I've seen some people bring them really big. And when you opened up a new checking account at the bank, they often gave you a free calculator. It might have lasted a week before it, died on you. But calculators did not have the ability to do certain things for a really long time. It took a long time for the technology really to excel. Calculators didn't have square roots the first couple of years. So I wanted to do a calculation. My calculator could add, subtract, multiply, divide. I could get decimals, but I couldn't take square roots. So I want you to approximate, let's say, the square root of 90 to 2 decimals. I need a 2 decimal place, just really quick and dirty, really crude for what I'm doing. I just need a couple places. I don't want to guess. But let's say I don't have a calculator with a square root key. Go, who wouldn't? Well, the first few hundred years of this, they didn't exist. Or maybe I'm out and about and I actually just simply don't have a calculator even. Can I still do this problem? Actually, yes. So I just need to take a derivative except there's a real small problem here. I gave you a function over there. We don't have a function. We need to create one. Would you agree that I'm trying to find the value of x if it's square root of 90? Yes? So what would x squared be? So what would x squared minus 90 be?
0.
Have we figured out our function? Yeah. Let's call our function x squared minus 90 and figure out when it equals 0. Isn't that what we just did over there? I gave you the f of x and we figured out when it equals 0 to 3 places. So let's do this. So we just created the function that we need, and the answer to our question will be when this function equals 0. Okay? Now, I'm not a rocket scientist, but I play one on TV, right? 90 is between 81 and 100. It's between 9 squared and 10 squared.
Mm-hmm.
So what would a really good starting point be?
9.5.
How about 9.5? I think that would be an excellent starting point. Okay? What is f prime of x?
2x.
So if I wanted to do x minus the function over 2x and write it as one quotient, that would make things a little bit easier. 2x over 2x, so I'd have 2x squared minus x squared minus 90 over 2x, and what would that be?
X squared plus 90 over 2x.
Okay, that's the thing I'm actually going to use. So let me go over here to the left. Anytime you're doing the Newton's method, you want to state what this ends up being. So in our case here, we're going to state what we are going to find. The n plus first iteration, therefore, is the nth squared plus 90 over 2 times the nth. When I'm doing my scratch work, I don't bother putting the n's in yet. It just takes too long. I'm lazy. This is the entire problem right here. This is what I needed to do in order to be able to do my calculations. I could leave it in this form. That's correct. This just takes longer to enter. And if things take longer to enter and I use more parentheses, I could make arithmetic errors. There is one common error and one common error only. Does anybody know what it is?
Distributing the negative.
Distributing that negative is the one error that I see. Here's how you know you made the error. You get to the end of the problem and your answer's not close. You're going, my answer's not close. Oh shoot, I distributed the negative badly in the first step of the problem. That's where you gotta just be really careful here. It's not a hard step, but it does happen a lot. Okay, we agreed that x naught is 9.5. We're doing 1 decimal place. So let's calculate what is our first iteration. To 2 decimal places, what's our first iteration?
9.49.
9.49, everybody? And now, using 9.49 exactly, the rounded off 9.49, my second iteration is,
9.49.
I'll hold the phone. We got it on the first try? Yeah, we did. That's actually really common. We got the answer on our very first calculation. We confirmed it on our second calculation. Not bad, huh? Wow, that's kind of cool. It's what it is it's really, really powerful. I have been in many situations where this was absolutely critical. When I went back to school a number of years ago to do statistics at San Diego State, we'd often do problems where we had to solve, you had exponentials and logs, usually not trig, but a lot of exponentials and logs, things where you couldn't solve for the variable. It was not possible, all the terms in there. And the only way to answer the question would be Newton's method, but a lot of the students completely forgot. And sometimes even the instructors had forgotten. And I'd be showing them, okay, here's how you do it using Newton's method, and we get answers, and we get them really fast. And it's just so beautiful and so powerful. So if I needed a 2 decimal place approximation for the square root of 90, I would say the square root of 90, approximately 9.49. Now, I'm pretty sure I did this right. How about we take the square root of 90, shall we? When you take the square root of 90 to two places, what does your calculator have?
9.49.
And do you see the decimals on your screen? Aren't those the same decimals you just saw a moment ago when you did your calculations? Isn't that incredible? That the calculations were doing the same thing that the calculator produced when I get exactly the square root of 90. Had I wanted to go 3 places or 4, it probably would have taken me at least 1 extra step because the convergence is happening later.
I think it was the same. I did it for 3 and they were the same on 1 step.
You got it in 1 step on 3 also?
Yeah.
Part of that is because these were so darn close together. These were close on the first problem, but not quite as close. Now, what a lot of people like doing with Newton's method, they love leaving it as polynomials just because polynomials are so nice and happy and simple to work with. But polynomials, you might actually be able to factor. So I'd rather use this for things that are not polynomial in nature, things that are way worse, way scarier. Transcendental functions. Okay? So let's do one. And I think I just did this one a moment ago. We didn't solve it yet. I want to solve x equals cosine of x. And we do know if I graph these 2 graphs, we know they will intersect. Agreed? We know they'll intersect. We have no idea what the value is when they intersect, but we do know. So I'm going to just give you a real rough sketch. Okay. All right. They intersect somewhere out here. Now, I do know that is pi over 2. Agreed? What do you think a good starting guess would be? How big is pi over 2? A little more than 1.5? Remember, this isn't a polynomial where we're crossing between consecutive integers. This is I'm having two graphs intersect each other. What do you think a good starting point would be for this one, if that's a roughly 1.5? If I can't do pi over 2, if I can't do anything pi-ish without a calculator, how am I going to do pi over 4 without a calculator? Your starting point is a rational number. What would be a really good starting point if that's roughly 1.5? How about 1? Doesn't 1 seem to make a lot of sense right there? 1 would be a really good starting point because it's rational. Yeah, I could do 0.75, but again, this is not a polynomial crossing the axis. This is two curves intersecting each other. Yikes. So I just need to differentiate my function. Oh, wait a minute. We don't have a function yet. We need to create one. How am I going to do that? Is that true?
Yes.
So how about we pick that as our function? Isn't that what we just did over there? We just said, take a difference, figure out when the difference is 0, and now make that your function because you're trying to find the value of x. The value of x. It's only going to happen one time. All right? Let's do this one. And again, I'm trying to just get a good picture. I don't care what math class or physics class or chemistry class you're in. The number of decimals isn't as important as you got the right number. So let's say we're just going to go 2 decimals on this one. My experience is 2 and 3 is pretty much what anybody does. Rarely do you go beyond that because it's overkill. I was joking with one of my students yesterday. They just finished all their transfer apps. And I said, did they ask for GPA? He said, yeah. I said, so how many decimals did you give them? Did you give them like 10? Think about it. Does anybody give 10 decimal places when they're giving their GPA? I mean, you could. Probably 1. I mean, maybe 2. Do you think anybody's really interested in that 7th decimal place? Yeah, probably not. I think the integer that comes first is probably more important even than the number of places. So going multiple places really isn't important. I just want to have the right answer. So whether I go 2 or 10, my first couple decimals are still going to be the same thing. So let's start with the derivative.
Oh, it's 1. The derivative, 1 plus sine x.
1 plus sine x. So now when I do this part, you never have to make it into one quotient. I just think it's sometimes easier if you do. So if I do x minus, then this will be x times this, so x plus x sine x minus that whole quantity. So I'm going to distribute and get a plus sign there, right? Does anything combine or cancel?
The x.
I like that. So now I can say with certainty that the n plus first iteration is going to be x, a sine of nth number, plus the cosine of the nth number, over 1 plus the sine of the nth number. And again, those subscripts really are important. This is the only place you need to write them. Because when I'm replacing xn with x0, it's because I'm calculating x1 and so on. Now tell me about, we said we want to start with, a good starting point we said was 1. That just seemed to make sense. There might be a better one.
Should there be an x in front of the sine x?
Did I lose? Oh, yes. Good catch, Casey. Yes, you're right. Good catch. There should be an x right here. Oh, good. Yeah, later we would have said, why isn't this working? Good, good. I'm usually the only one that can't see it because I got tunnel vision right there. Good catch. Now, that's ugly. But we're only going a couple places.
Well, I mean, unless you're going out 4 places, it's 1 on this.
Unless we're going 4 places?
Yeah, unless you go 4 places out, you just get 1 back when you round it. It's 0.999984.
The final answer?
Yeah, for when you put it through the.
I don't think it's going to be 1. But let's just try it. So our starting point we said is 1. By the way, you could argue, well, 0.5 makes just as much sense. 0.75 makes just as much sense because remember, 1's crossing. I'm looking at my picture going, I just want a nice starting point. My starting point isn't going to be my answer. But what if I made my starting point, 10? What if I made my starting point, -5? Well, your starting point has to actually be relatively close. Otherwise, this could take you further away. We want every iteration to take us closer. So now, when you're doing this calculation, I haven't pointed this out yet, didn't we say this value on the x-axis is pi over 2? We didn't say this value on the x-axis is 90 degrees.
Yeah.
So therefore, what must your calculator be in?
Radian.
mode. Oh, if I'm in degree mode, my answer won't mean anything. It'll be crazy. You got to be in radian mode. Oh, now let's try it. Okay, so make sure your calculator's in radian mode first. Now we'll start with a 1. Okay, so sine of 1, 1. All right, tell me what you get.
0.75 in radian.
Hold on. Let me do my thing again. So make sure I got all this right. So this is 1 plus sine. Plus cos. So x sine plus cos. Okay, just making sure. All right, try this one. So I got 0.75. Did anybody else get that?
Mm-hmm.
Okay. A little further up. All right, so let's do 0.75 now. And what do you get now to 2 places?
0.74.
0.74. Ooh, that didn't change much at all. When that change is very small, my professional experience is we've probably hit the answer. But that's no guarantee. My next one might be 0.73. So I do have to do it again. You can't stop now. You have to have consecutive iterations produce the same thing. So does anyone do x3 yet? It's also going to be 7. So now, right, we can rejoice. We got the answer. We're pretty sure we did it right. So what are we saying now? The question was to solve this. Our answer is x is approximately 0.74. This check is as easy as it can get. All I need to do is take the cosine of 0.74. Here's my check. What is the cosine of 0.74? To 2 decimal places, it is 0.74. So is the cosine of x essentially equal to x at that value? To 2 places, it is. The actual answer is probably like 7.4 or 7.39 something. It's infinitely many, but to 2 places. We got it on our second iteration, confirmed it on our third. Everybody cool with that? So Newton's method is how I find solutions to problems that I could not find otherwise. I can't solve it algebraically. There's no inverse trig. There's nothing I can do to solve it when I have a trig function and an algebraic function, or an algebraic function and a logarithmic function, or something like that. All of these things require that I would do some version of this. Now, if you know how to program the computer, you can do a lot of this on the computer, but it's still doing the same calculation. This is just doing it faster. But you have to tell it what calculations to do. So, let's try another one. Let's do, I want to know, when does this equal this? There's my e to the x. There's the line y equal x plus 2. I have more than one solution, so I have to decide which one I want. I cannot find multiple solutions at the same time. I can only find one at a time. So let's find this one here. Okay? I don't know where that is. What is e to the first power? Just e. 2.7 something or other? So if I replace x with 1, these are already pretty close, aren't they? So what do you think a really good starting point would be?
1.
How about 1? I don't want to start with 5 or negative 3. This value is not 1, but 1 is really close. Agreed? So we'll start with x0 equals 1. I'm going to put that here. Now, I don't have anything else yet, so I need to do all my setup. But that's always a good starting.
If we do choose like a crazy number for x naught, should it still like work eventually?
This is a good question. This is a very good question. In the situation where there's only one answer to the question and you start really far away, it is very possible that you come back. It just takes a little while. What's bad though, if there are two possible solutions and you start too far away, you may end up getting the other one. In other words, I have two solutions here. I don't want this one. I wanted that one. But if I start too far to the left, I may converge to that one. If I make an error, here's one of the ways you know you've made an error. I got a positive number, then I got a negative number, then I got a positive number, then I got a negative number. That's actually not possible. That means that I probably did the bad job of distributing or something. If my numbers, you have a fairly good idea because you had a starting point that was reasonable. And as you're doing your calculations, your numbers are getting further away from that. That's bad. That's a clear indication, okay, something's not right. And again, it's some arithmetic mistake probably early on. Or I'm just doing a lousy job with my calculator using parentheses, right? Parentheses on top, parentheses on bottom. But if you're finding your numbers are getting, the difference between them is getting smaller, that's a good thing because that means I'm closing in on something. You really don't know until you've done a few problems and you start seeing trends. So I'm just saying kind of obviously, if I put a 1 in here, these are really close, so 1's probably a really good starting point. Now I need to do my setup. I need to be able to get the function that I'm going to work with. There it is. Right there. You don't have to draw the picture, although I think a lot of times the picture helps us understand what it is we're saying. That picture is not, perfect, but it's fairly representative. And I'm looking for the one in the first quadrant. So I need a function. What do you want to call our function?
X plus 2 minus e to the x.
So you want to call it x plus 2 minus e to the x. Then our derivative is
1 minus e to the x.
1 minus e to the x. So x minus the function over the derivative. That's what I need to use. Now, I'm going to make that into one quotient because I can see at the very least the x's will cancel if I do that. So I'm going to get x minus x e to the x and subtracting the whole numerator. I'm going to write it out so I can't possibly mess it up. Well, okay, I could possibly mess it up. Everybody okay with that? Now let's clean that up. Those will cancel. And what am I left with? Negative x e to the x, negative 2 plus e to the x, all over 1 minus e to the x. That's what I'm going to use. And now I'm going to write it out formally. This is my scratch work so that I can state this part clearly. The n plus first iteration is negative nth iteration e to the xn minus 2 plus e to the xn all over 1 minus e to the xn. So I have a lot of places I've got to put, I wish there was some really simple stuff I could do with that quotient, but there isn't because I have two terms in the denominator. So I just got to be careful. I have a calculator. There's nothing hard about this. I just got to be careful when I'm entering. So we're going to start with 1. So, by the way, it doesn't matter if you're in radians, right? So replace x with 1 and let's see what we get. What do you get as your first calculation? Anybody?
1.164.
Oh, we didn't say, let's go 3 decimals this time. Okay, sorry about that. I really should have said that first. So 1.164, beautiful. So I moved a little, I didn't move a lot. And by the way, so the question is, how do I know I'm on the right track? I don't, but I only moved a little. If my next movement is smaller than that, that's a really good sign. If my next movement is more than that, that's a bad sign. It means I'm somehow getting away. So let's use this for the next one. This one got to go a little slower because the E key sometimes takes a little while. Negative 1 point, oops, negative 1.164. So anybody got a number?
1.239.
Yeah,
Different number?
1.146.
1.146.
Anybody get a different number?
Wait, hold on, I didn't do this.
That's what I got.
You got two of the same numbers.
Did you get 1.146?
Yeah.
Okay.
Yeah.
If Chase got it, we kind of have to go with it.
Yeah, of course.
Yeah, I actually got the same thing. The E's can be a little trickier. Remember the parentheses. That's the other thing that'll just kill us if we don't close. So that movement was significantly less. Is that a good thing? Yeah, that makes me feel like we're doing the right thing. If my movement was more, or if it took me on the other side of 1, that would make me a little suspicious. Only because we're not really zeroing in. Let's do that one then. Oops. 1.46 times. My calculator keeps sticking. It's driving me nuts. Anybody have a number? I have a very happy number.
Mm-hmm. Same.
I got the same number. Twice in a row. Rejoicing should be taking place all over the place. So, question was, solve this. This is your calculations. This is all of your work. This is not your answer. You haven't answered the question yet, but what's the answer going to be? It's going to be 1.146. You're not going to say my answer is x3. No, x3 is your third iteration. My answer is x is approximately 1.146. That's my answer. I'm pretty sure I did it right. What are you going to do now? Do it. Or I do what Bella did, do the difference. It's probably easier if you do this. Do the difference and what should you get? A number very close to what? 0. So let's do that. So 1.146 plus 2 minus e to the 1.146. And when I do that, my calculator My calculator says it's approximately 1, 2, 3 zeros. That's a really good answer. To 3 decimal places, that is 0, isn't it? So that's a very powerful calculation right there. All right, this is Newton's method. Okay, go ahead and stop that. I'm going to tell you.
Feel about that, Jake.
Okay, question. Seems like a fairly simple question. I'm telling you the derivative of a function is 2x. I'm asking you what the original function was. That's not real hard, is it?
No.
What do you think?
X squared plus c.
Okay, well, we all agree x squared, right? But see, Max wants x squared plus 3.
B.
But
C.
Bella wants x squared minus e. And Gail, just to be clever, she wants x squared plus 3 pi. Are they all correct?
Maybe.
Are all of those possible answers? Yeah. In fact, would you agree there's an infinite number of possible answers? Because Chase said, I'm going to put a plus c where c represents what we call an arbitrary constant. Any constant I put there would make this a true statement because when I differentiate, the constant will go away. But I don't know what the constant is, so I'm going to put a plus c. I can find the constant if I'm given something called an initial condition. Okay? So, I'm going to answer this question. Okay? Here's the answer to the question. We have y equals x squared. And we have, let's say, x squared plus 1, x squared plus 2, x squared plus 3, and maybe this one. Okay, you guys know what this is, right? I affectionately call it the candelabra of parabolas. Try saying that 3 times fast. It's like the new drunk test now. Candelabra of parabolas. All of those are answers to this question, aren't they? What if I wanted one specific answer? What if I also included and f of 1 equals 3? What if I included that also? Now would there be more than one answer? How many of these go through the point 1, 3? At most, 1, because they don't intersect. So it's probably right there is 1, 3. So if I said this, now let's go back to this statement here. F of 1, which equals 1 squared plus c, must equal 3. What does that make c equal to? 2. Now I've found what's called a particular solution. We found at first what's called a general solution. If I'm given an initial condition, then I can find the particular solution. More often than not, you're not even going to have an initial condition. So you just stop here and you don't worry about it. Okay? What we did was we went backwards. Think baby algebra for a minute. You learned how to multiply polynomials out, and that's pretty mindless. I'd multiply them out, I get other terms. Not a lot of thought. But then I give you a polynomial and I say, what things did I multiply that gave me this? And that's a much higher level of reasoning. Now you had to factor to go in reverse. To take a derivative, if I have all my derivative formulas in front of me, there's no derivative that I should be challenged by. It's never going to be hard. I just use the formula, maybe there's a chain rule. But if I said, here's the result, where did it come from? That's a higher level of thinking. And later when we throw in the chain rule, it's a much higher level of thinking. What we did, going forward, we take a derivative, we call that differentiation. In reverse, it's called integration. When I use differentiation, the answer is the derivative. When I use integration, the answer is the antiderivative, right? The dark side of calculus, I would call it. This is a higher level of reasoning. If you can go this way, then derivatives are actually easy. Derivatives are always supposed to be simpler, but if you've mastered derivatives, you have all of your derivatives down, you are pretty clear every time. Yeah, you might have to double check the formula, but you have differentiation down. Then this process is usually not that taxing, okay? So how do I show this from a notation standpoint? So let's talk about the derivative notation going forward. F of x equaled x squared plus c, we just said. F prime of x is the derivative of x squared plus c, correct? d dx is a single symbol, it's not a quotient. It's a symbol that says, take the derivative with respect to x of whatever follows. By the way, d dx can't come after, it doesn't work that way, right? That's the notation that says, find the derivative. What is the notation that says, I want to go the other way around? So first off, we're going to introduce something called the integral. This symbol is called an integral. Some folks like to say it's an elongated S. I guess to some degree. That's not bad. It's this symbol here. What goes here is called the integrand. The integrand is my argument, much the same as this is the argument. That's the thing I'm differentiating. The integrand is the thing I'm finding the antiderivative of, or I'm integrating. And then I put in the dx. The dx says I'm doing it with respect to x. In the same way this dx says I'm differentiating with respect to x. The most important part of the entire process is this. Because I can put any letter of the alphabet there, just like I can put any letter of the alphabet here. If this is not an x, it means x is a function of this variable. Right? d dt, we've already done that. Oh, that means chain rule. If I put a letter other than x here, that means, again, similar things. In this class, we will not have different letters here. Calc 3, they have different letters here because they have multiple variables. We will always have the same letters. But these don't have to be the same. We've already done this. Right? That's what the chain rule is. These aren't the same if I'm using the chain rule. So, in this problem, I had a 2x. I'll move the dx a little closer. This says, find the antiderivative of this function with respect to this variable, and you all told me it was x squared. That was a fairly simple thing because I gave you something that you could easily conceptualize. What we're going to do is have an antiderivative formula that matches every one of our derivative formulas, and then there's actually a few more. And we're going to learn these over the course of the next few weeks, and then we're going to do all sorts of crazy cool applications of this. Okay, questions so far? We good? All right. So, it works like this. What do you think? It's almost an ODA, isn't it? If the derivative of sine x is cos x, then the antiderivative of cos x kind of has to be sine x. But there's one more piece I always throw on. Plus c, because I want to account for every possible answer. An antiderivative is not unique. Only an initial condition will not make it unique. If I don't have an initial condition, then I don't worry about the value of c. It just goes along for the ride. But it is part of the answer. And that's confusing at first, because if I drop the plus c, I haven't said something that's wrong, but then down the road, that value might not be 0. You never assume it's 0. In fact, it's safer to assume it's not 0. I just don't know what it is, and it's probably not important at the moment. It will become important later. Okay, does that make sense? So, how about if I do this?
U prime of x plus c.
Wow, it's pretty easy, huh? So, if I know the derivative going forward, by the way, no chain rule. We have to master this without chain rule. What did we do with our derivatives at first? We learned how to differentiate x to a power, sine, cosine. Then we started throwing in compositions. Oh, function to a power, sine of a function, e to a function. Then we worked in the chain rule. So we want to master the antiderivative of functions of just x. We got to get that first. Because then when we throw in the chain rule, things get a bit more complicated, but we'll have a complete picture. And most things do involve the chain rule in both directions. Okay? So, here's what we do know. Are there any restrictions on this problem? Is that true for every real number n?
Yes.
Yes. There are no restrictions on that. None whatsoever. So don't tell me an answer. Let's see if we can figure it out, though.
N plus one.
Are we in agreement that it makes perfect sense to add 1 to the exponent if I'm decreasing the exponent by 1? But is it I don't know. Let me put A. I don't know what A is. I'm gonna put a number there. There is definitely a number here.
Okay.
So here's what I want you to do. I want you to differentiate this and see what we get. If I differentiate this, well, the C is going to go away, and I'm going to get A times n plus 1 times x to the n.
Yeah.
Well, what does that have to equal?
Excellent.
That has to equal x to the n, doesn't it? Huh. So that means this whole quantity has to equal 1, which means that A must be,
1 over n.
oh. Well, that's interesting. So if I asked you to integrate x cubed, you know it's x to the 4th times the 4th. Does that make sense? Oh. So if differentiating means I bring the exponent down as a coefficient, decrease the exponent by 1. Now I am increasing the exponent by 1 and then putting the reciprocal of that guy here. Well, why am I doing that? Because what happens when I differentiate this? Won't the 4 cancel with the 1/4? Yes? You agree? Yeah. So that's an easy one. That's our first true formula that we've just figured out. Now, there's a couple more that are extremely important. Okay? I'm going to remind you of something we know that is hugely important. In words, the limit of the sum is the sum of the limits. The limit of the scalar multiple is the scalar multiple of the limit. We know both of those are absolute. We have a limit of a product, limit of a quotient, limit of a composition, but none of those apply to derivative, do they? These are the only two that apply to derivative. So let's state what they are now in terms of derivative. How about the derivative of f of x plus g of x? We know is f prime of x plus g prime of x. We know that. So in words, the derivative of the sum is the sum of the derivatives. We know the derivative of a scalar multiple is the scalar multiple of the derivative. Those are very powerful statements. Only the sum and scalar multiple go from limit to derivative. Well, it turns out they also go to antiderivative. And we'll prove it. I want to integrate f prime of x plus g prime of x dx. This is a formal mathematical proof we're doing, which is extremely powerful. When we first learned derivatives, we learned them one term at a time, and then we used the definition of the derivative, which was really gnarly. But then when I said differentiate this entire polynomial, you can't look at the entire polynomial at one time, but we showed you can differentiate one term at a time. Well, if I'm going to integrate a large sum of things, wouldn't it be nice if I could just integrate one term at a time? But we don't know that yet. But what do I absolutely know? Shouldn't I get the integrand back again? Plus c. Why? Because the derivative of f plus u is this. Now, let's compare that to the following. What does this equal? Well, the antiderivative of the derivative should be the function. Do you agree? The antiderivative of the derivative has to be the original function, but plus a constant. I'll call it C1. And then what's the antiderivative of this guy? And then plus a constant. By the way, absolutely you make these different constants. It's a 1 in infinity or 0 probability that they could be the same constant. They can't be the same constant. It's actually mathematically impossible. But if I put plus c, then I'm saying they're the exact same number always. They're never going to be the same number. That could be negative 10, that could be positive 5, I don't know. Okay, how about if I rewrite this like this? C1 represents any arbitrary constant. C2 represents any arbitrary constant. So therefore, isn't their sum still an arbitrary constant? So why don't, I don't know, let's give it a new name. How about we just call it C? Did we get that back?
Yeah.
We just proved that the integral of the sum was the sum of the integrals. That's huge. That is absolutely astronomical. So that means when I'm integrating a bunch of stuff, I can literally look at it one term at a time. Secondly, let's look at the second one. What about scalar multiples? I want to integrate the scalar multiple of f prime of x dx. Well, I know what it's supposed to be. It's supposed to be k times f of x. Everybody agree? This is supposed to be k times f of x. I'll just say plus some arbitrary constant. Now, if I do this, won't this be k times f of x plus some c? By the way, the c I get here can't be the same as the c I get here because these two functions are not the same. What's this? So the integral of a scalar multiple is the scalar multiple of the integral. That is a very, very, very powerful thing. That will simplify and shorten a lot of the processes because I don't have to worry about certain things. The most common thing we're going to work with in this class, and really all the classes, are polynomials. Those are the most common things. So here's what I want to do. Let's start with it. I want to integrate 4x squared minus 3x plus 5. Now, according to what we just did, it's the integral of the sum is the sum of the integrals, and the integral of a scalar multiple is the scalar multiple of the integrals. So technically, we could break this all the way down. Do you agree that that is true? I broke it up and I pulled out all the scalars. I don't want to do that. That's too much work. But it's correct. Now, what's the antiderivative of x squared? Well, it's x cubed times, got it over there,
1/3.
times a third. All right. The antiderivative of x to the first power would be x to the second power times half. The antiderivative of 1.
X.
X, because when I differentiate x, I get 1. So far, so good?
Mm-hmm.
So my answer is 4/3 x cubed minus 3/2 x squared plus 5x plus c. This is the answer. Everything I did was true and correct. Here's what I want. I want to go to there. I want to go to there 100% of the time without exception. I don't ever want to do the in-between because we don't have to. Once we understand what's going on with the process, you can almost always go directly to the answer. How do I do that? Well, let's do a similar problem. I've got 6x to the 4th minus 3x squared plus 5x. All right. I'm going to differentiate each one at a time. I'm not going to rewrite the problem as 3 integrals. But I know I have 3 things in my answer. What's the antiderivative of x to the 4th? X to the 5th times 1/5, but I already had a 6, so it's 6 times 1/5. What's that?
605.
Before you take another step, check in your head. If I differentiate this, the 5 comes down, cancels, and leaves me 6x to the 4th. Okay, good. I check as I go. I don't check after the fact. I want to check as I go to catch errors if they're there. Will you make mistakes? Yeah, everybody's going to make mistakes, but they're usually simple to find. So you catch what I did? I'm now looking at the 6. I increased the exponent by 1, brought it down. It was already times 6. Beautiful. Increase the exponent by 1.
3. No, 3.
Times the 3rd, but I already had a 3, so it's just a 1. Quick check. 3x squared. Okay, good. X to the
Squared.
2nd power times a half, but I already had a 5, so times 5 halves. And then finishing off with a. That's what I want you to do, what I just did. Did I take any extra steps whatsoever? Did I do steps in my head? No. I integrated each of these one at a time. The mistake a lot of people make when they're doing this is they focus on the coefficient. Don't focus on the coefficient. Coefficient is just going along for the ride. Whatever your answer is, it's going to be multiplied by the coefficient. The coefficient has nothing to do with the antiderivative. The antiderivative had to do with what's here. Oh, x to the 5th. Okay. The 6 is just getting multiplied by that. A lot of times we focus on the wrong thing and then we mess up the answer. So I just did the first problem a second time, but I didn't rewrite it. I just did it directly. But I mentally check as I go just in case. You're gonna make mistakes, that's okay. What you wanna do is catch them and then eliminate them, because this is the majority of calculus. Technically, the definition of calculus, believe it or not, the definition of calculus starts with the integral. So in the strictest sense, the old school books, the really old books, would call what we've done the first 8.5 weeks pre-calculus. I disagree, because we're doing limits and derivatives, which is all part of calculus. But the term, the word calculus itself refers only to the integration part. But you can't do differentiation without integration. They go hand in hand, do they? So I think they're all together. All right, let's try another one. I think that's 4. Do those coefficients in any way affect how I'm going to answer this question?
No.
No, they only affect what my final answer is going to be in terms of the coefficients on my final answer. It's only the functions that matter. So I don't want you to memorize. Here's how I want you to answer the question. What function, when I take its derivative, gives me secant squared? Tangent. Therefore, this is 3 tan x. Always do it in that way. Then you don't have to actually remember a whole separate set of functions. When I said the derivative of sine is cosine, so the antiderivative of cosine is sine. Yes, they go hand in hand. The derivative of tangent is secant squared, so the antiderivative of secant squared is tangent. What function, when I differentiate it, will give me negative cosine? Negative sine. If you look at it that way, aren't you really only thinking about the derivatives?
Would there be a +4 sign?
Did I
+4 now?
did I lose one?
Well, it's
No,
negative
negative
4
and negative.
times negative sine x. So is it gonna be a +4 x or +4 sine x?
Well, what's the derivative of sine? So what's the derivative of negative 4 sine? Yeah, we're good here. The plus and minus was important. The 4 was just a coefficient. It just went along for the ride. But do you notice how I asked the question? Rather than ask you what are antiderivatives of formulas, which you will all know in time from just repetition, it's much easier to say what function's derivative looks like this. Then how did I start all this? I said what function's derivative looks like 2x, and you all told me x squared. You didn't even think about it. It was automatic. You were doing an antiderivative without even knowing that's what I was asking you for. And by the way, there is a reason we do it this way, and I've explained this to many people recently because they're asking, why do we do things in certain orders? You're a kid. Addition and multiplication make sense. Subtraction and division are very confusing because they're artificial. Why? Because none of the 11 properties of algebra apply to them. There's no commutativity, associativity, distribution, none of those. There's no closure, there's no those. But how do you introduce them? Because it's necessary to know. So we said like this. 4 plus what number equals 6? 4 plus what number equals 6? 2. I just taught you how to subtract, by the way. Because what's your answer? 6 minus 4. That's how you learned, by the way, that's how all human beings pretty much learn subtraction. It's called the missing addend approach. I set it up as a sum, but didn't tell you what was missing, so you actually have to subtract to get the answer, but you didn't know you were subtracting yet. 4 times what number equals 12? That's how you learn division, by the way. But I set it as a product, yeah. 4 times what number is 12? 12 divided by 4 is the answer, isn't it? But you were thinking about it as multiplication because that's way easier. 4 times what is 12? You filled in the 3. You didn't do a division, you didn't even know it existed yet. So what function's derivative looks like secant squared? Well, tan, duh. Did you realize you were integrating when you answered that question? No, but that's how we introduce it because it's much easier for your brain to take that route. Over time, you will know all your antiderivative formulas because they're just the derivatives in reverse. But right now, I want you to think about it as just what's the missing derivative approach. Right, like I just said, with the missing addend and the missing multiplicand. That's actually a word. It's a terrible word. Okay? Let's do a good one here. If I asked you to differentiate this, would you differentiate it in this form?
No.
What would you do?
Negative 4 times x to the negative third
Okay.
dx.
By the way, is this a true statement? I didn't ask if it's useful. Is it true? Yeah. Well, it turns out that's exactly what I want to do for integration. I want to write it as an exponent because now my answer is going to be x to what power? To the negative 2. I'm adding 1. The reciprocal of negative 2 is negative a half, but I already had a 4, so that's now my quick check. Negative 2 times negative 2 is 4. I decrease it. Okay, good. So far, so good?
Mm-hmm.
That wasn't complicated, but it was a little different because I had a negative. Is this a good final answer?
Probably won't put x on.
Not quite because we have a negative exponent, so what's the best final answer?
Negative 2 over x squared plus c.
Beautiful. That wasn't that bad. When do you think it gets really icky?
When e to the power of x on top.
No, not the e. Not for exponents. Come on. What's your least favorite? My least favorite. Roots. Oh. Yeah. I've got 3 times the cube root of x squared. Something like this. Like, oh, yuck. Can you integrate this as is?
No.
Yeah, I don't want to. I want to change this to what?
3x.
To the
2/3.
2/3. At this point, do I even care that it's a fraction? Do I even care that this is a negative exponent at this point? No, I'm just going to add 1 to the exponent. That's pretty simple. It doesn't matter that it's an icky number. You're just going to add 1 to the exponent. But you're going to do that before you worry about the coefficient. So when I add 1 to the exponent, what will the new exponent be? 5/3. So it's times 3/5. Times 3 would be 9/5. Quick check. 5/3. Okay, boom. Can I leave the answer in this form? Do I have to rewrite it as a root?
Leave it if you're gonna keep working with it.
I'd probably leave it. I don't know that there's any advantage. If I'm going to continue working with it, here's another reason why you want to leave it like this. Do you have this key on your calculator? No, but you have an exponent key. So that's one of the reasons probably you want to leave it as a fractional exponent because of that. So far, so good? Okay. Let's do one that's truly diabolical, shall we? Okay. You had this question on your first exam as a derivative. And most people really, really struggled with it because they made the problem so incredibly complicated. And then you looked at the key and you went, oh my gosh, really? Well, it's not actually possible to integrate that expression. That expression, as is, has no formula. But if I had asked you to differentiate this, I want you, because a lot of times, whatever we did for the derivative often works for the integral, right? We had to change this in the same way we would have changed it for the derivative. What's the easiest way to attack this problem? Make it the derivative of what? What's
Part.
that of that?
Minus 3x, 1/2 power.
2 minus 4. Negative. Have I done any calculus yet? No. I asked this question on the test. What was interesting is nobody did that. And I think I even asked a second derivative, which means the second derivatives got kind of ugly. So what's the answer here? 8x plus 6x to the negative third. So it's 8x plus 6 over x cubed. I would want that to be really simple and direct. Could I do it by using the quotient rule and do it the long way? Yeah, it just takes a lot more steps. But now I want to integrate this. I can't integrate this. There's no quotient rule of integration, unfortunately. But what should I do? Integrate that. So I'm going to ask you a really simple but very important question. Is this quantity here identically equal to this quantity here? Are they identically equal?
Yes.
They're not equal unless, I'm not like losing any part of the domain. I didn't do anything. There's nothing canceled. They're identically equal. That's why their derivatives have to be the same, but it's way easier to differentiate this. So do you agree that that integrand and that integrand are absolutely identical? Hopefully you do. But I can easily integrate that one, can't I? Because now I just got to look at the exponents. All right, anybody feeling fast here? Fire out the whole answer, if you will.
4x to the third over 3 plus 3 over x plus c.
It's, yeah, 4/3 x cubed.
Wait, what's the last one? You were so fast.
Plus 3 over x plus c.
Oh, you've already moved it. Now what's here?
4/3.
4/3, yeah. There's no over 3. Your denominator cannot be a number. There is no mathematical statement where you would ever put a denominator as a number. You don't have a quotient. You have a fraction. I'll give you a simple example. This would be gnarly to do calculus on because I would have to use quotient rule. I'd have to use all sorts of rules. But my denominator is not a function. You only have a quotient. Only have a quotient. Absolutely across the board without exception. Only have a quotient if your denominator is a function. This is 1/2 x. This derivative has to be quotient because you wrote a quotient. This derivative is just 1/2. There's never going to be a time in life where you would choose to do this. There's no advantage. In fact, there's extreme disadvantages. No, these are the same, and that's the correct answer because I don't have a quotient. I have a constant in the denominator. And I want to remind people because when I'm doing derivatives or antiderivatives, I don't want to create quotients. That just makes things harder. But fractional exponents are totally okay. When I go to do this derivative, last thing in the world, you want to put a 5/9 in the denominator here? Hopefully not. No, my denominator is a function, so that definitely is a quotient. Well, that was a quotient. Now, the final answer, by the way, most of you said plus 3x to the negative first, then you moved it downstairs. I don't really care, because that wasn't that complicated. But that's excellent if you can do that seamlessly without having to take any of the in-betweens. I want to eliminate the in-betweens. I did a problem earlier when I wrote it out in multiple steps. I showed you every step that's actually taking place. Now I'm showing you how to fast forward to the last step. You're not skipping anything. You're not doing anything in your head. The other steps were sideways. I was not going forward. I was literally rewriting the problem. Sometimes you have to rewrite the problem. I had to rewrite the problem. I can't do this problem, but I can do this one. But other times, rewriting the problem by, well, let me rewrite it now as two integrals. Now let me rewrite it by factoring out the coefficient. That's a complete waste of time, because you can go right to the answer at that point. All right, now we're going to solve what's called a differential equation. We have a whole class of these. It's called Math 255. I teach that next semester. Differential equations. That sounds just terrifying, doesn't it? Oh my God, differential equation. All right. By the way, the very first thing I wrote today, was what? F prime of x equals 2x, and you told me f of x equals x squared plus c. Am I right? That was the first thing we did. That is a differential equation. Would you say that was pretty easy? Differential equation just means you have an equation involving a derivative. That's all it means. And in order to answer the question, you have to integrate. That's what a differential equation is. These are not differential equations. I'm giving you an integral and saying evaluate it. This doesn't equal something else. See what I mean? I'm not saying this equals something else. I'm just saying integrate this. You're just doing straight up integration. But if there's an equation involved and I'm solving the equation, that's a differential equation. So here's the differential equation. Excuse me. I'm going to tell you that the second derivative of a function is 12x squared, how about minus 6x minus 4 times the cosine of x plus 3e to the x. We'll make this really, really hairy. I'm also going to tell you that f of 0 equals 5, f prime of 0 is negative 12. These are called initial conditions. What do you think I want you to find? I'm telling you f double prime of x. What do you think I want you to find?
F of x?
I want you to find f of x. Ooh. By the way, will there be some c's along the way?
Mm-hmm.
Yes. Will I be able to find them?
Yep.
Actually, I will because of the initial conditions. I can't tell you what they are yet. Now, this is about as gnarly as you can get. In my 255 class, this would be a fair challenge for them, but you know everything you need to know to answer this question. Can I start by finding f of x? No, but what can I find? I can find f prime of x. How did you get f prime? You differentiated f. How did you get f double prime? You differentiated f prime. Oh, so how do I get f prime back again? I integrate this guy. Let's write it down. Okay. We have all of the tools we need. We just don't know what order yet to do them in. So I can say with certainty f prime of x is equal to the antiderivative of 12x squared minus 6x minus 4 cos x plus 3e to the x dx. You guys want to try this? Well, this is how I would do it. Get the exponent first.
4 minus 3x squared.
So I get the exponent first. Okay, good. So how about the next one? Plus or minus?
Minus source sine.
Good.
Plus
The only one you can't possibly make a mistake on.
Yes.
See, not only is e to the x its own derivative, it's also its own antiderivative. We really like e to the x's. Now, how many times am I going to integrate in this problem?
One more
Altogether.
time. Or twice.
I'm going to integrate twice, so how many constants am I going to get?
2.
2. So I should label them something different. Some people say A and B, I'll say C1 and C2. This is very important. If I call them both C, then I am saying in absolute terms they are the same value. It would be really unlikely that they're the same value. Now, before I move on and do another antiderivative and have 2 unknowns in my answer, can we find the value of C1 right now?
Mm-hmm.
What are we going to use?
You plug 0 into x and then you solve for the difference for c.
Yeah, I'm going to use that fact right there. I said that the first derivative evaluated at 0 is negative 12. So here's what we're going to do. What is f prime of 0? Well, it's 0 plus 0 plus 0 plus 3 plus C1. Everybody cool with that? And what is that equaling?
Negative.
So therefore C1 is C1 is negative 15. Good. Okay. So I can now say, I'll write it again just so I don't lose it. I probably don't really need to write again, but I don't want anybody to say, where'd that come from? Minus 4 sine x plus 3 to the x minus 15. Okay. Can I now say f of x equals? It's going to be the antiderivative of this.
X to the fourth.
Well, okay, let me write it down first. You're too fast. Okay, so x to the fourth times 1.
Minus
X to the third times, well,
1.
1. I'm liking this one so far. I know I have a cosine. Okay, I know I have a cosine. I know I have a 4 cosine.
Plus 4.
Is it positive or negative?
Positive.
It's always easier now to ask derivative. The derivative of positive cosine is negative sine, so that's a plus. Here's the problem we have. The antiderivative of sine is negative cosine. The derivative of sine is positive cosine. That's hard to remember. So I like doing sines and cosines by thinking, what's the derivative? Because I already know the plus or minus.
You left the exponent 4 on the
Oh,
first
thank
line.
you. Thank you. Because the derivative of this is this.
Plus 3 e to
Yeah,
the
I'm
x.
pretty sure we got that one.
Minus 15x.
Minus 15x
Plus c.
plus c2.
2.
Do we have that information somewhere on the board? Uh-oh, I have a cap. I have a cap, but oh, here we go. What's that? This guy right here? F of 0 equals 5, so we'll put that right here. So f of 0 is 0 plus 0, 4.
3. 0.
0, C2. And that whole thing is 5, so that means C2 is
Negative 2.
Negative 2.
negative 2. So going back to the original, the answer to this question is x to the fourth minus x cubed plus 4 cos x plus 3 e to the x
Minus 2.
minus 15x minus 2. Can I check this?
You take the derivative of it twice.
I would have hoped that you guys had checked it along the way. Well, not only take the derivative twice, but also check the initial conditions. Because when I take the derivative twice, does everybody agree that these two terms are going to disappear?
Mm-hmm.
So if I take the derivative twice and I get this back, then I know this part's correct, but that doesn't mean that this was necessarily correct. So now I'd use my initial conditions. Real quick check. At 0, I'd have 0, 0, 4 plus 3 plus 0 minus 2, that's 5. Okay, good. Now I do my first derivative, same thing. Now I do my second. This is a big problem. Was it hard? No, just a lot of stuff. This is called a second order differential equation because you solved a second derivative. You actually have that skill, 45 minutes into your first day of integrating. Not bad, huh? So what should you be able to integrate? Well, really, if you go to your derivative list, you have a lot of functions in their derivatives. You should be able to integrate everything that you can go in one direction or the other. And what I mean by that is you don't have to use any technique whatsoever. Whew. Oh my goodness. Well, right off the bat, you're looking at the 6 and going, what function has a 6? None of them do. 6 is a What if I do this? Mentally pull the 6 out of the problem. Can you think of any functions whose derivatives look like 1 over 1 plus x squared?
Hyperbolics.
No. It is recent. Really recent. Actually, one of the most recent ones. In fact, how recent is it? Did you just turn in a quiz with this one? No, this was a couple quizzes ago. Inverse tangent. I don't know what within the last couple of quizzes. Oh, the derivative of inverse tan looks like 1 over 1 plus x squared. So what's the answer to this question? It's inverse tan of x with a 6 in front. When you have a coefficient and it makes everything look wonky, I would say mentally pull it out of the problem because the coefficient has nothing to do with the answer. It's just multiplied by your answer. So we did know the antiderivative of this, but if your mind was stuck on the 6, you might have been in trouble. Now, did we have to do anything clever? No, that's exactly the formula. What we're doing today are things that look exactly like the formula. There's no technique involved. Now, having said that, where are we now? Yeah, okay. The next 2 days, we're going to be doing essentially the same thing. In Calc 1, there are the first half of the class, the single most important thing you learned was chain rule. Because that applies to every derivative, doesn't it? When I'm differentiating a composition of functions, right? Not the sine of x, but the sine of a function of x, e to a function of x to a power. Everything we did involved chain rule. That was the most important thing from the first half of the class. We're going to do the chain rule for antiderivatives over the next 2 days because it's considered the most important thing basically for the second half of the class. But if you ask anybody in the Calc 3 class, they'll say, what is the single most important thing you learned in Calc 1? It will be what we're doing the next 2 days because it's the thing you use the most often. You do more integration than differentiation down the road. So the chain rule as it applies to integrals becomes huge. Doesn't mean that it's hard, but it means it's really important and really widespread. So we're going to look at so many different examples, but that's all exam 3 material, not exam 2. That's why it's the first thing we do for exam 3. It gives us quite a long time to get good at it. Will you get good at it? You have to. I've taught calculus for about 1,000,000 years. It's not possible to pass calculus without absolutely mastering both forms of the chain rule. Because that's most problems you will ever do the rest of your life in calculus will be derivatives or integrals, always involving the chain rule. So we will go over things over and over and over. You'll get good because you don't have any choice. You'll get good just because you're going to do so many things and everything starts looking the same. Even though all the functions are different, the processes start feeling the same, going, oh, yeah, we always do this first. So when you were doing derivatives, if your argument wasn't an x, you knew you do chain rule. And then you just multiply that at the end. That became automatic. Now when we're doing antiderivatives, it's going to have a similar feel. And a lot of times you're going to say, oh, I have to consider the chain rule. And then here's how I do it. It's a little bit more complicated. But you will get good at it because we're going to do it so many times. Okay, we're just not one and done. Now, we are done with the exam 2 material as of today. Our exam is like 1,000,000 years from now. It's like,
The Monday before Halloween.
is it even this month?
It's the 30th.
The 30th, okay, it's barely this month. It's quite a long ways away. I don't know that I've put the key of the practice test up yet. Okay, if someone would just send me a quick email, remind me, because I need to do that for both calculus classes. I'll have that up today. It is very wise to hit the practice test before the weekend. We're going to review a week from today, but it's always good to have a head start on that to make sure that you're on top of things. So next week you can ask all of your questions, right, to make sure. Now the exam is still quite a ways away. Okay, but we're finished with all the material today. We got 12 days. And so the last 2 quizzes, right, last day and today are obviously the quizzes you're turning in next week. It is also wise to redo those quizzes. Now, a fair question, and one that gets asked, my stats students have a test tomorrow. They were asking this yesterday. Is material from the first exam going to be on the second exam? Not the same questions, no. Your ability to differentiate is on the second exam. But you did a bunch of derivatives on the first exam, very specific types of derivatives, right? Polynomials, trigs, all these things. For this exam, the only derivatives I think we had were the inverse trigs and the hyperbolics. Those were the main things. So those are the ones you're going to be asked. But obviously your ability to differentiate, right, is on the line here, because this test is mostly applications of the derivative. All of your graphing techniques and all this involve being able to differentiate and such, but not necessarily complicated functions. Okay? Newton's method and very, very basic antiderivatives. Very basic antiderivatives. Nothing harder than this are going to be on the next test. And so it's a test, hopefully, but believe it or not, the antiderivatives will be one of the highest percentage areas. Because I'm going to give you a polynomial and say, what's the antiderivative for you? You're not going to have any trouble. What's the antiderivative of a sine or a cosine? You're not going to have any trouble on that. No chain rule, nothing complicated. Because it's intro today. And then we hit the ground running the next, the next few lectures. Any questions? All right, go ahead and stop that.